Chapter 5 Periodic Classification of Elements. In class 9, we have learned that matter around us is present in form of elements, compounds and mixtures, and the elements which contain atoms of only one type. Do you know how many elements are known till date? At present, 118 elements are known to us. All these have different properties. Out of these 118, only 94 are naturally occurring. Out of 118, only 94 are naturally occurring. As different elements are being discovered, scientists gathered more and more information about the properties of these elements. They found it difficult to organize all that was known about the elements. They started looking for some pattern in their properties, on the basis of which they could study such a large number of elements with ease, making order out of chaos. Early attempts at the classification of elements. We have been learning how various things or living beings can be classified on the basis of their properties. Even in other situations, we come across instances of organization based on some properties. For example, in a shop, soaps are kept together at one place while biscuits are kept together elsewhere. Even among soaps, bathing soaps are stacked separately from washing soaps. Similarly, scientists made several attempts to classify elements according to their properties and obtain an orderly arrangement out of chaos. The earliest attempt to classify the elements resulted in grouping the then known elements as metals and non-metals. Only the elements which were known at that time. Okay? Later, further classifications were tried out as our knowledge of elements and their properties increased. Topic 5.1.1 Dauber-Near's Triads. Sorry for the pronunciation. In the year 1817, Johann Wolfgang Dauber-Near, a German chemist, tried to arrange the elements with similar properties into groups. In the year 1817, Johann Wolfgang Dauber-Near. He identified some groups having 3 elements each. So he called these groups triads. He identified some groups having 3 elements each and he called them triads. Dauber-Near showed that when the 3 elements in a triad were written in the order of increasing atomic masses, the atomic mass of the middle element was roughly the average of the atomic masses of the other 2 elements. So, if 3 elements were written in a triad, the middle element's atomic mass was average of the other 2 elements. For example, take the triad consisting of lithium, sodium and potassium with the respective atomic masses: lithium 6.9, sodium 23 and potassium 39. What is the average of atomic masses of lithium and potassium? How does this compare with the atomic mass of sodium? So as you can see, the average of 6.9 and 39 is almost equal to 23. So the average of lithium and potassium, which are the first and third elements, is equal to the atomic mass of the second element, which was sodium. And this triad consists of 3 elements, that is lithium, sodium, potassium. First lithium, second sodium and third potassium. Given below, table 5.1 are some groups of 3 elements. These elements are arranged downwards in the order of increasing atomic masses. Can you find out which of these groups form Dauber-Near's triad? In the table 5.1, group A elements N, P, As have the atomic masses 14, 31, 74.9. Group B elements are Ca, Sr, Ba with atomic masses 40.1, 87.6, 137.3, and group C elements are Cl, Br and I with atomic masses 35.5, 79.9 and 126.9. You will find that group B and C form Dauber-Niers triads. Dauber-Niers could identify only 3 triads from the elements known at that time. Hence, this system of classification into triads was not found to be useful. Only 3. Johann Wolfgang Dauber-Niers, 1780 to 1849. Johann Wolfgang Dauber-Niers studied as the pharmacist at Münchberg in Germany and then studied chemistry at Strasbourg. Eventually, he became a professor of chemistry and pharmacy at the University of Jena. Dauber-Niers made the first observations on plutonium as a catalyst and discovered similar triads of elements which led to the development of periodic table of elements. Okay, in table 5.2 you can see Dauber-Niers triads. First is Li, second element Na and third is K. This is first triad. In second triad, first element is Ca, calcium, Sr and Ba. In third triad, first element is Cl, second Br and third I. Just memorize this one table somehow. Newland's law of octaves. Topic 5.1.2. The attempts of Dauber-Niers encouraged other chemists to correlate the properties of elements with their atomic masses. In 1866, John Newlands. Okay, so you can see that Dauber-Niers' first name was Johann, John, whereas Newland's first name was John, John. Okay. In 1866, John Newlands, an English scientist, arranged the then known elements, the elements which were known then, in the order of increasing atomic masses, the same way Dauber-Niers did, in the order of increasing atomic masses. He started with the element having the lowest atomic mass, hydrogen, and ended at thorium, which was the 56th element. He found that every 8th element had properties similar to that of the first. He compared this to the octaves found in music, therefore he called it the law of octaves. It was known as Newland's law of octaves. In Newland's octaves, the properties of lithium and sodium were found to be same. Sodium is the 8th element after lithium. Similarly, beryllium and magnesium resemble each other. A part of the original form of Newland's octaves is given in table 5.3. Newland's octaves, as you can see, you don't technically have to remember each and everything. Yeah. Are you familiar with musical notes? In the Indian system of music, there are 7 musical notes in a scale: sa, re, ga, ma, pa, dha, ni. In the West, they use the notations do, re, mi, fa, sol, la, ti. The notes in a scale are separated by whole and half-step frequency intervals of tones and semitones. A musician uses these notes for composing the music of a song. Naturally, there must be some repetition of notes. Every 8th note is similar to the first note, and it is the first note of the next scale. It was found that law of octaves was applicable only up to calcium, as after calcium every 8th element did not possess similar properties to that of the first. It was assumed by Newlands that only 56 elements existed in nature and no more elements would be discovered in the future. What a egoist! Only 56 elements, he just said it. like no more elements can be discovered possibly. But later on, several new elements were discovered whose properties did not fit into the law of octaves. In order to fit elements into his table, Newland adjusted two elements in the same slot, but also put some unlike elements under the same node. Can you find examples of these in the table 5.3? As you can see that cobalt and nickel are placed in the same slot and are in the same column as fluorine, chlorine and bromine, which have very different properties than these elements. Iron, which resembles cobalt and nickel in properties, has been placed far away from these elements. With the discovery of noble gases, the law of octaves became irrelevant. Thus, Newland's law of octaves worked well with lighter elements only. Questions. First, did Dauber's triads also exist in the columns of Newland's octaves? Compare and find out. Well, as you can see, the first triad, lithium, sodium and potassium, the first triad is indeed placed in the Newland's octaves. As for the other two triads, Cl and Br, which is the third triad, are also placed together, but the third element, which is iodine, is not placed among them. Same goes for the second one. Sr and Ca are placed in the third slot in Newland's octaves, which are the second triads, but another element in the same triad, that is Ba, is not placed among these two. Second, what were the limitations of Dauber's classification? Now, the biggest drawback was that Dauber's could only find 3 triads, which means only 9 elements. Also, the law was not holding good for elements having very high mass or very low mass, and not all the groups obeyed the Dauber's triad law, and those were the limitations of Dauber's classification. Third, what were the limitations of Newland's law of octaves? First of all, Newland assumed that there would be only 56 elements, no more than that. All the other limitations are: first, several elements were fit into the same slots in Newland's periodic classification. Example, cobalt and nickel were placed in the same slot. Second, elements with dissimilar properties were grouped together. Example, halogens were grouped with some metals like cobalt, nickel and platinum. Third, Newland's law of octaves held true for only up to calcium. Elements with greater atomic masses could not be accommodated into octaves. And fourth, the elements that were discovered later on could not fit into octave pattern. These were the limitations of Newland's octaves law. Topic 5.2, Making Order Out of Chaos, Mendeleev's periodic table. Even after the rejection of Newland's law of octaves, many scientists continued to search for a pattern that correlated with the properties of elements with their atomic masses. The main credit for classifying elements goes to Dmitry Ivanovich Mendeleev. Dmitry Ivanovich Mendeleev, a Russian chemist. He was the most important contributor to the early development of a periodic table of elements wherein the elements were arranged on the basis of their fundamental property, the atomic mass, and also on the similar chemical properties. Dmitry Ivanovich Mendeleev, from 1834 to 1907. Dmitry Ivanovich Mendeleev was born in Tobolsk in Western Siberia, Russia on 8 February 1834. After his early education, Mendeleev could join a university only due to the efforts of his mother. Dedicating his investigations to his mother, he wrote, "She instructed With example, corrected with love and travelled with me to places spending her last resources and strength. She knew that with the aid of science without violence, with love but firmness, all superstitions, untruth and errors can be removed. The arrangement of elements he proposed is called Mendeleev's periodic table. The periodic table proved to be the unifying principle in chemistry. It was the motivation for the discovery of some new elements. How was it a motivation to discover elements? How was a table a motivation? When Mendeleev started his work, 63 elements were known. He examined the relationship between the atomic masses of the elements and their physical and chemical properties. Among chemical properties, Mendeleev concentrated on the compounds formed by elements with oxygen and hydrogen. Mendeleev concentrated on compounds formed by elements with oxygen and hydrogen. He selected hydrogen and oxygen as they are very reactive and formed compounds with most elements. The formulae of the hydrides and oxides formed by an element were treated as one of the basic properties of an element for its classification. He took 63 cards and on each card he wrote down the properties of one element. He sorted out the elements with similar properties and pinned the cards together on a wall. He observed that most of the elements got a place in a periodic table and were arranged in the order of their increasing atomic masses. It was also observed that there occurs a periodic reoccurrence of elements with similar physical and chemical properties. On this basis, Mendeleev formulated a periodic law which states that the properties of elements are the periodic function of their atomic masses. What a beautiful statement. They're going to ask this question, alright. By heart this sentence. The periodic law was, the properties of elements are the periodic functions of their atomic masses. Well, here it means that depending on the atomic mass, after a certain period or after a certain gap among the elements, the properties repeat. Now I don't know why the sentence is structured in this way, but this is what it means. As I said, Mendeleev's periodic table contains vertical columns called groups and horizontal rows called periods. Ooh, it's a huge table. Mendeleev's periodic table was published in the German journal 1872. In the formula of oxides and hydrides at the top of the columns, the letter R is used to represent any of the elements in the group. Note the way formulae were written. For example, the hydride of carbon CH4 is written as RH4 and the oxide CO2 is written as RO2. Topic 5.2.1 Achievements of Mendeleev's periodic table. While developing the periodic table, there were a few instances where Mendeleev had to place an element with a slightly greater atomic mass before an element with a slightly lower atomic mass. The sequence was inverted so the elements with similar properties could be grouped together. For example, cobalt, atomic mass 58.9, appeared before nickel, atomic mass 58.7. Looking at table 5.4, can you find out one more such anomaly? Here is another one in the table. As you can see, the atomic mass of V is 50.94 and the atomic mass of Cr is 50.20. So according to his rules, we should be placed after Cr, but it is not. Further, Mendeleev left some gaps in his periodic table. Instead of looking upon these gaps as defects, Mendeleev boldly predicted that the existence of some elements that had not been discovered at the time. Wow! So he's basically saying that these gaps are not defects. Somebody is going to discover a new element which is going to fit into these gaps. Wow! Mendeleev named them by prefixing a Sanskrit numeral Eka 1 to the name of preceding element in the same group. For instance, Scandium, gallium and germanium, discovered later, have properties similar to Eka boron, Eka aluminium and Eka silicon. Remember these sequence-wise. Eka boron for scandium, Eka aluminium for gallium and Eka silicon for germanium. Silicon is silver, germanium is like when you imagine germanium, you can imagine silver. Same. Then Eka boron, so boron, scandium. I don't know, man, just remember this sequence wise. Boron, scandium, aluminium, gallium, silicon, germanium, respectively. The properties of Eka aluminium predicted by Mendeleev and those of element gallium, which were discovered later and replaced Eka aluminium, are listed as follows. Table 5.5. Properties of Eka aluminium and gallium. Table 5.5. Property. Atomic mass of Eka aluminium is 68. Atomic mass of gallium is 69.7. Remember, these Eka aluminium is the gap that Mendeleev left, and he claimed that whatever element this gap is going to fill, it is going to be similar to aluminium. That's what he said. Formula of oxide of Eka aluminium is E2O3 and gallium is Ga2O3. Formula of chloride for Eka aluminium is ECl3 and gallium is GaCl3. They are the same, and that's what he said. This provided convincing evidence for both the correctness and usefulness of Mendeleev's periodic table. Further, it was the extraordinary success of Mendeleev's prediction that led chemists not only to accept his periodic table but also recognize him as the originator of the concept on which it was based. Noble gases like helium, neon and argon have been mentioned in many a context before this. These gases were discovered very late because they were very inert and present in extremely low concentrations in our atmosphere. One of the strengths of Mendeleev's periodic table was that when these gases were discovered, they could be placed in a new group without disturbing the existing order. Limitations of Mendeleev's classification. Electronic configuration of hydrogen resembles that of alkali metals. Like alkali metals, hydrogen combines with halogens, oxygen and sulfur to form compounds having similar formulae as shown in the examples here. While in other hand, just like halogens, hydrogens also exist at diatomic molecules and it combines with metals and non-metals to form covalent compounds. What it means here is that alkali metals are placed on the left side of table, but halogens are placed on the right side of table. So here hydrogen is like alkali metals, but it is also like halogens. So now it becomes difficult to place hydrogen as it combines with diatomic molecules and it combines with metals and non-metals to form covalent bonds, which is the property of halogens. Activity 5.1. Looking at its resemblance to alkali metals and the halogen family, try to assign hydrogen a correct position in Mendeleev's periodic table. Second, to which group and period should hydrogen be assigned? Now the reason we can't place hydrogen in any one of the groups, so we basically give it a special position, as you will see in the periodic table. Okay. Certainly no fixed position can be given to hydrogen in the periodic table. This was the first limitation of Mendeleev's periodic table. He could not assign a correct position to hydrogen in his table. Isotopes were discovered long after Mendeleev had proposed his periodic classification of elements. Let us recall that isotopes of an element have similar chemical properties but different atomic masses. Similar chemical properties but different atomic masses. Therefore, same atomic number. Activity 5.2. Consider the isotopes of chlorine Cl35 and Cl37. Would you place them in different slots because their atomic masses are different, or would you place them in similar position because their chemical properties are same? Thus, isotopes of all elements posed a challenge to Mendeleev's periodic law. Another problem was that atomic masses do not increase in a regular manner in going from one element to the next. So, it was not possible to predict how many elements could be discovered between two elements, especially when we consider the heavier elements. Questions. First, use Mendeleev's periodic table to predict the formula for the oxides of the following elements. Now for this one, you just need to check in which group does an element lie. As for the first one, K, which is potassium, lies in the first group, and in first group the oxide would be R2O, that would be K2O. So the oxide of potassium K is K2O. In the similar manner, find out for all the other elements. Second, besides gallium, which other element have been discovered that were left by Mendeleev in his periodic table? That would be germanium and scandium, or is it scandium? Scandium. Third, what were the criteria used by Mendeleev in creating the periodic table? The atomic masses of the elements and their capacity to form compounds with hydrogen and oxygen was used. Fourth, what do you think the noble gases are placed in a separate group? Because they were discovered later on, so they are placed in a different group and their valency is also different. Topic 5.3, Making Order Out of Chaos, the Modern Periodic Table. In 1913, Henry Moseley showed that the atomic number symbolized as Z of an element is a more fundamental property than its atomic mass. Accordingly, Mendeleev's periodic table was modified and atomic number was adopted as the basis of modern periodic table, and the modern periodic law can be stated as follows. Properties of elements are a periodic function of their atomic mass. Atomic number, which means that after a certain period, a gap between elements, according to their atomic number, the properties were similar, if that makes sense. Let us recall that the atomic number gives us the number of protons in the nucleus of an atom, and this number increases by 1 in going from one element to the next. Elements, when arranged in order of increasing atomic number, lead us to the classification known as modern periodic table. Prediction of properties of elements could be made with more precision when elements were arranged on the basis of increasing atomic number. Activity 5.3. First, how were the positions of cobalt and nickel resolved in the modern periodic table? Cobalt and nickel were placed in separate groups. How were the positions of isotopes of various elements decided in the modern periodic table? Well, we did not have to worry about isotopes because since they were arranged in based on atomic number, one element was given one slot. So even if it had isotopes, it still remained in the same slot. Third, is it possible to have an element with atomic number 1.5 placed between hydrogen and helium? Well, no, because an element cannot have atomic number 1.5 as the protons cannot be 1.5. They're very small, there are like 1 or nothing, no in between, only integers. As we can see, the modern periodic table takes care of 3 limitations of Mendeleev's periodic table. The anomalous position of hydrogen can be discussed after we see what are the bases on which the position of an element in the modern periodic table depends. 5.3.1 topic. Position of elements in the modern periodic table. The modern periodic table has 18 vertical columns known as groups and 7 horizontal rows known as periods. Let us see what decides the placing of an element in a certain group and period. Activity 5.4. Look at the group 1 of the modern periodic table. Name the element and name the elements present in it. Well, there is actually only one, that is hydrogen. Write down the electronic configuration of the first 3 elements of group 1. I'm so sorry. It's not hydrogen, it's lithium, sodium and potassium. Hydrogen has still not been given a position. If you see properly, there is a gap between lithium and hydrogen. It's not given a position yet. So the first group has lithium, sodium and potassium, and their atomic configuration would be of lithium 2,1, of sodium 2,8,1, of potassium 2,8,8,1. How many valence electrons are present in 3 elements? The answer 1. You will find that all these elements contain the same number of valence electrons. Similarly, you will find that elements present in any one group have the same number of valence electrons. For example, fluorine, chlorine belong to group 17. How many electrons do fluorine and chlorine have in their outermost shell? Fluorine's electronic configuration is 2,7, so the valence electrons is 1, and same for chlorine, it's 2,8,7, so the valence electrons is 1 because they need 1 electron to form 8 in the outer shell. Hence, we can say that groups in the periodic table signify an identical outer shell electronic configuration. On the other hand, the number of shells increases as we go down the group. It means as we go down the group, as we go across the as we go down the group, we see that first for lithium it was just 2,1, that were 2 shells. Then for sodium it was 2,8,1, so 3 shells, and for potassium it was 2,8,8,1, so 4 shells. Number of shells increases as we go down the group. There is an anomaly when it comes to position of hydrogen because it can be placed either in group 1 or group 17 in the first period. If you look at the modern periodic table, you will find that the elements Li, Be, B, C, N, O, F and Ne are present in the second period. Write down their electronic configurations. You can do that by yourself. Do these elements also contain the same number of valence electrons? Not at all. Do they contain the same number of shells? Yes, they do. You will find that these elements of second period do not have the same number of valence electrons, but they contain the same number of shells. You also observe that the number of valence shell electrons increases by 1 unit as the atomic number increases by 1 unit, moving from left to right in a period. Or we can say that atoms of different elements with the same number of occupied shells are placed in the same period. Na, Mg, Al, Si, P, S, Cl and Ar belong to the third period of the modern periodic table, since the electrons in the atoms of these elements are filled in K, L and M shells. Write the electronic configuration of these elements and confirm the above statement. Each period marks a new electronic shell getting filled. Yeah, sorry about that. You know what, I'm not apologizing. That was very good. How many elements are there in the first, second, third and fourth periods? We can explain the number of elements in these periods based on how many electrons are filled into various shells. You will find how many elements are there in the first, second, third and fourth period. We can explain the number of elements in these periods based on how electrons are filled into various shells. You will study the details of this in higher classes. Recall that the maximum number of electrons that can be accommodated in a shell depends on the formula 2n square, where n is the number of the given shell from the nucleus. For example, K shell 2 into 1 square, which is equal to 2. Hence the first period has 2 elements. L shell 2 into 2 square is equal to 8. Hence, the second period has 8 elements. The third, fourth, fifth and sixth and seventh periods have 8, 18, 18, 32 and 32 elements respectively. The reason for this you will study in higher classes. The position of an element in the periodic table tells us about its chemical reactivity. As you have learned, the valence electrons determine the kind and number of bonds formed by an element. Can you now say why Mendeleev's choice of formulae for compounds as the basis for deciding the position of an element in his table was a good one? Because oxygen has the configuration 2,6, so it has only 2 valence electrons and hydrogen has only 1. Since there are so many elements can form bonds with them, and so he chose these compounds for deciding the position of an element. How would this lead to elements with similar chemical properties being placed in the same group? Topic 5.3.2 Trends in the modern periodic table. Valency. As you know, the valency of an element is determined by the number of valence electrons present in the outermost shell of an electron. Activity 5.6. First, how do you calculate the valency of an element from its electronic configuration? Second, what is the valency of magnesium with the atomic number 12 and sulfur with atomic number 16? Similarly, find out the valencies of the first 20 elements. Fourth, how does the valency vary in a period on going from left to right? Fifth, how does the valency vary from going down a group? Answer these yourselves, whatever. Atomic size. The term atomic size refers to the radius of an atom. The atomic size may be visualized as the distance between the center of the nucleus and the outermost shell of an isolated atom. The atomic radius of hydrogen atom is 37 pm. Picometer. 1 picometer is equal to 10 raised to minus 12 meter. 1 picometer is equal to 10 raised to minus 12 meter, and the distance between the center and the outermost shell, that is the radius of hydrogen, is 37 pm. Let us study the variation of atomic size in the group and in a period. Activity 5.7. Atomic radii of the elements of the second period are given below. Period 2 elements. Atomic radius of B 88, BE 111, O 66, N 74, Li 152 and C 77. Arrange them in the decreasing order of their atomic radii. Are the elements now arranged in the pattern of the period in the periodic table? Which elements have the highest and lowest at largest and smallest atoms? How does the atomic radius change as you go from left to right in a period? You will see that the atomic radius decreases in moving from left to right along a period. This is due to an increase in nuclear charge, which tends to pull electrons closer to the nucleus and reduces the size of the atom. Activity 5.8. Study the variation in the atomic radii of first group elements given below and arrange them in an increasing order. Group 1 elements: Na, atomic radius in pm 186, Li 152, Rb 244, Cs 262, K 231. Name the elements which have the smallest and largest atoms. How does the atomic size vary as you go down a group? Answer these questions yourselves. You will see that the atomic size increases down the group. Atomic size increases down the group. This is because new shells are being added as we go down the group. This increases the distance between the outermost electrons and nucleus so that the atomic size increases in spite of increase in nuclear charge. Metallic and non-metallic properties. Activity 5.9. Examine elements of the third period and classify them as metals and non-metals. On which side of periodic table do you find the metals? On which side of periodic table do you find the non-metals? You will see that on the left side you find metals and on the right side you find non-metals. As we can see, metals like Na and Mg are towards the left hand side of the periodic table, while non-metals like sulfur and chlorine are found on the right hand side. In the middle we have silicon, which is classified as a semi-metal or metalloid because it exhibits some properties of both metals and non-metals. In the modern periodic table, a zigzag line separates metals from non-metals. The borderline elements boron, silicon, germanium, arsenic, antimony, tellurium and polonium are intermediate in properties and are called metalloids or semi-metals. As you have seen in chapter 3, metals tend to lose electrons while forming bonds, that is, they are electropositive in nature. Activity 5.10. How do you think the tendency to lose electrons changes in a group? How will this tendency change in a period? As the effective nuclear charge acting on the valence shell electrons increases across a period, the tendency to lose electrons will decrease. As the nuclear charge increases, the tendency to lose electrons decreases. Down the group, the effective electric charge experienced by a the effective nuclear charge experienced by valence electrons is decreasing because the outermost electrons are further away from the nucleus. Therefore, these can be lost easily. Hence, metallic character decreases across a period and increases down a group. Metallic character decreases across a period and increases down a group. Non-metals, on the other hand, are electronegative. They tend to form bonds by gaining electrons. Non-metals gain electrons. Metals lose electrons. Activity 5.11. First, how would the tendency to gain electrons change as you go from left to right across a period? Most metals are present at the left side of the period and non-metals are present at the right side of the period. So the tendency to gain electrons will increase as you go from left to right across a period. Second, how would the tendency to gain electrons change as you go down a group? Since metallic character increases down a group, the tendency to gain electrons will decrease as you go down a group because metals give electrons and non-metals take electrons, and metallic character increases as you go down the group. As the trends in the electronegativity show, non-metals are found on the right hand side of the periodic table towards the top. These trends also help us to predict the nature of oxides formed by the elements, because it is known to you that oxides of metals are basic and that of non-metals are acidic in general. Questions. First, how could the modern periodic table remove various anomalies of Mendeleev's periodic table? First one is position of hydrogen, second one is placement of isotopes, and third one is keeping elements of higher atomic mass before the elements of lower atomic mass. All of these were taken care by the modern periodic table. You find out how. Okay, first one, hydrogen is given a special place in the modern periodic table. We don't have to worry about isotopes because in a single slot a single element is placed, no matter how many different masses, atomic masses it can have. Since these are placed according to atomic number, we don't have to worry about atomic mass. So it does not matter if an element has higher atomic mass or a lower atomic mass compared to the other one. Second, name two elements you would expect to show chemical reactions similar to magnesium, beryllium and calcium, since they belong to the same group, and in a group the chemical properties are similar. Third, name A. Three elements that have a single electron in their outermost shell. lithium, sodium, potassium. B. Two elements that have two electrons in their outermost shell. Magnesium and calcium. C. Three elements with filled outermost shell. Neon, helium, argon. Fourth. A. Lithium, sodium, potassium are all metals. They react with water to liberate hydrogen gas. Is there any similarity in the atoms of these elements? They have the same number of valence electrons. B. Helium is an unreactive gas and neon is a gas of extremely low reactivity. What, if anything, do their atoms have in common? Their atoms' last shells are completely filled, so they are very unreactive.